Good evening, June 1st, 2023. Uh, the field of differential analysis is quite grand, and it starts with the calculus itself, the differential, the integral, and then gets into the systems that are so defined as functions that are functions recursively of their own differentials and functions thereof. Differential analysis. It's a deep field. I wish I better knew it. I haven't very well studied it. Uh, the courses in it are along lines of ODEs and PDEs, and after calculus, calculus 2, and vector calculus and advanced calculus, and for examples. And then there's dynamical modeling, and then systems like probability theory, of course, where probability theory is quite involved with distributions that many involve the functions as are of the exponential, which is its own antiderivative, and so very common in solutions to differential equations. There really is an idea to find what are approaches to plane curves that are of the various forms that fulfill being solutions to differential equations, those being their integral equations and as regards to differential equations and their solutions. And then finding values of those is for the initial value problems and boundary value problems, vis-a-vis finding classes of curves by their genus and rank or what, and these kinds of things. With regards to the surfaces they so define, that's been a large context of this these monologues, is that the exact complementarity, the dual of, in the one sense, is that we have plane curves and their integral equations, or differential curves and their solutions, which are the plane curves in a sense, and then finding solutions for those given values, plugging in values and getting out values of functions. The objects under treatment are functions, and so define these curves and this and that. That it's as part of analysis, it's is relevant to know the derivations to go into things, and to know then where it's possible to, for example, select a numerical method and then approximate, get as close as you want to a value, which is the usual goal of estimating or predicting values, or that otherwise things must emit a closed form solutions, and that if they don't, then there's no analytic tractability in the sense of the symbolic analysis, that's the goal. So there for one field, it's got various perspectives and various goals, and lots of things go into what time and effort it takes to learn any particular one of those. Why, in a general sense, that it's easier to start with, or to carry the route for the average person who's not necessarily sure how they're going to apply differential analysis to the linear curriculum, to the course that arrives at these are our methods. After calculus, then we're going to talk about differential equations, and then we're going to talk about superpositions of solutions and these kinds of things, and linear systems, and the linear, and how it's possible then for ordinary equations to make up solutions for those, and establish the existence, the uniqueness of solutions, and plug those in and get those out, and various notions like the determinants and discriminants and the Wronskians and other factors of the linear terms that are also complemented by that the linear analysis is already in the curriculum, and these other tools are already in the curriculum. For the Fourier analysis, that's all the trigonometry is already in the curriculum. That otherwise, when we get to where something like the integral calculus of the integral equations of the plane curves, that are differential equations, these integral equations, kind of reflects as well that that's where it ends up learning a whole variety very common and useful and well represented and classically constructible things that involve a lot more of specific knowledge compared to a wide body of general knowledge, and especially when it arrives at that the goal is like, well, in the general standard way, it arrives at some point in time you're able to still achieve both goals rather like so, in that there are numerical methods very closely attached to all these linear approaches. And so if you give up, you can crunch out the numbers this way. And because otherwise still the goal is usually to find a closed form solution, because then it can be computed directly in a closed form. And so if that can be figured out, then that's still preferable and still a good thing. So, indeed, then a lot of times in the competitions of things, the end result is that it will just be crunched out to get close enough, and then that will be an estimate and approximation and and it's fine. Now, then in these other things where it gets into seeming to start with dealing with various families of plane curves, then how they can add together and they can have this completeness property. Well, what's this completeness property? Well, this completeness property is about reconstructing a function as a sum of other functions. So the Fourier analysis is all about that. Sine and cosine are orthogonal functions. There's a variety of ways to sort it out so that if you have a classical function, a classical continuous function, it can be in a given bounded interval defined with this boxing of its region where it's analytic, and this windowing, this windowing of this region, this boxing of it above and below, so that it exists and then it converges at any one of these points. And there are discussed various things that go into the definition of the integration and the continuous and the piecewise and that it's complete, that it can reconstruct via an infinite series of sine and cosine the function of interest. And so then a large part of its content can be brought in. And kind of like with these Fourier sums, is like, and there's like, and if the Dirichlet kernel in the first few terms don't get very close, you can kind of widen it out with the Fourier terms, and hopefully then that will bring in some more of its character. And you can, so these are means to start saying, here's a spigot. A spigot is as of a cask. You can open the spigot and out comes the contents of the cask. And so a spigot algorithm is basically different than an extraction algorithm. An extraction algorithm is kind of like, well, you can compute the billionth digit of pi with the two-phase digit extraction algorithm without having to compute everything in the middle. That the spigot algorithm is, well, starting at the beginning, you can crunch out numbers and gather the analytical character and so on and go along this way. Now, this is where there's a closed form of sorts for each of the coefficients of one of these series for the Fourier type analysis, Fourier-style. But most of the analytical character is contained in the higher, respectively lower order terms, in terms of what then is for an infinite series of terms that it's complete in that it so follows that by adding all those out, they come back to a thing. So is that a closed form? Yes and no, because usually when you think of closed form, it's also finitely many terms. So if you can get that from finitely many terms to an infinite series, and then back to finitely many terms, which is much the goal of differential geometry's development of the immersions and submersions. It's to figure out this completeness and specifically the truncating part. But coming back again, then something like the Fourier analysis or the other applications of transforms, because then in the differential analysis there's much employment of transforms. Fourier's transform, the Henkel's transform, Mellon's transform, the Z transforms, wavelet transforms. Wavelets are their own original thing with their own kernels, their own singular things. Wavelets are very general. There are many different functions that is the mother of all wavelets. Vis-a-vis waves, of course, which when we think of waves, there's the sinusoidal waves are the most common models of the equations of wave motion. And there are others, and they've been under discussion. But coming back again, the idea is that for these notions of the completeness, is that to use a different aspect of the field for that, these other families of functions, or these other kernels, gets into that they have to reconstruct each of the steps that come up and into the approach, from the definitions of integration, after the definitions of numbers, and arithmetic and algebra pretty well, calculus in the fundamental theorems, as to what is the integration in terms of its regions of analysis, its regions with analytical character, that then when it goes back to trying to figure out that for these different plane curves and families of plane curves, excuse me, and their reconstruction is the idea that there's all kinds of different waveforms and other orthogonal functions and other means that can build to them, as long as you can figure out in an analytic way that something grows until it fills the whole area. Like an infinite-sided polygon is a circle, or segments of an orange go to make it from when it's round to when it's a triangle. As well as you can imagine that something would translate, interpolate between such form condition A and such form condition B, that it would be possible then in terms of those differences, that the most minuscule and scale of those differences add up in a pattern to reproduce any way you can think of gearing a thing like a spirograph, and reproduce whatever other curve that arrives up. Has that for some of the curves, there are different systems that A can complete it in a what we might call Fourier-style analysis, which is reconstruct it as a family of functions and be able to determine an infinite series of its coefficients and establish the convergence properties and the existence properties and the convergence properties again, and the existence properties and the values that these removable discontinuities or the piecewise are for the definition of the integration, really. So there's this completion, and then also there's sometimes it'll be in closed forms. It's like, well, what's the Fourier series of the sine wave? Well, it's real simple. It's just like a Fourier series of any other function, except the coefficient is 1, and only in the first term it has a coefficient, the rest having a 0. That's so it has a closed form to be able to prove then that. Or also as well to be able to figure out, it's like, well, if we can establish this closure and under the same conditions of the convergence and stuff. Now, I'm not familiar with too many approaches that do this, called mixing transforms, or what the idea being that for any particular contrived form, you can say, well, if you take the one series of a Fourier style and this another one of a Henkel or Mellon style, and subtract them, that is a curve. Whether or not it's contrived to be anything of particular interest or modeling any real quantity is something else, but they exist. And so then the idea is it's to be figured out is like how to work up for these corner and edge cases. What are the sums and terms in these products? They end up being an addition formula because they end up then just being means to interpolate from the trivial solutions, like the flat line of all zeros, or in this identity dimension in the quadrant octants half planes dimension, a space, is an example for making up then in the course of the analysis that the examination of the linear curriculum provides a lot of the desiderata and requirements of what would be necessary to make such a formally as rigorous a thing, a mathematical thing, that all the guarantees of mathematics will provide it with validity. And B, it's more apropos in some cases. And C, it's just that there is an outside the box, and in the case that there are many ways to fill the box, and that in this manner, what results is looking for those which explore what are exposed as conventions that are otherwise taken as constants. Because they're conventions, they're opinions, or they're the results of intermediate developments. Like, well, I'm glad you've studied this part of the theory in the standard linear curriculum for 5 or 6 years, because we're going to have to use all of it just to have a convention. Right? There are others. And so getting back into this in kind of the converse is that, well, one way to look at the conventions is once you have a line continuity, and then you make a field continuity on that, and then you have a signal continuity over that, which are kind of like 3 ways to get completeness, even establishing the existence of the continuous domain via a numerical setting, and a setting of algorithmics, a setting of magnitudes, and as well as signs in magnitudes. That starts as a lot more concrete already. That is more than the entire standard linear curriculum has, which is field continuity. And putting those together involves various concessions then, these bridges or the ponts between them, which are just so involved. They're not intractable, they're not unsensible. To be fungible, they need their definitions. But it's not so bad when it arrives at it. Well, at least for the integer and non-integer part, you can treat the line reals as the non-integer part, as long as you can just have them going from 0 to 1, and they're continuous in how they go from integer to integer, just like the field reals do. When you can frame something like that, then you can talk about them having equivalent results. Besides that, when you have, like, what are the line elements of a line integral? Well, they're kind of like points in a line. Does it really make sense to define a difference between points in a line, as this line drawing, and points on a line, as the field's points, or classical geometry's constructions points also, when you come down to it? Because classical geometry has no notion of the drawing of a line, the act, only its fait accompli, only when it's exists or before and after it exists. There's no notion of time in classical continuous or classical geometry and its constructions, just order and existence. So that gets into then that at least that establishes a pretty firm basis for the continuous domains. Because then to get into some notions of the definitions of completeness of these functions, of continuous functions, is, for example, as already was shown, for any of these different families of orthogonal functions according to a weight, where the product of under the integral of these two functions for different numbers is 0, and that their weight has that the integral of this function for a given number by the weight is 1. And so sine and cosine are great. They have these properties, orthogonality of these functions. So just like that applies, and so something like the Fourier analysis can be applied to any pair of orthogonal functions as so defined and derived, when there's also enough identities and otherwise known about the functions that the other things that go into the derivations of the Fourier-style analysis can be carried in and brought up, because establishing a convergence and this and that makes use of these very well-known properties of geometry and stuff like the small angle approximation. That's one of its big things. Compared to that, like the semicircle curve or whatever, it's when it reaches the axis, the semicircle, it's vertical. Compared to when sine reaches it, it's like 1. These kinds of things, sine theta or however it may so be, that fact of it that makes for that where it's crossing, it's used in the derivations for the Fourier-style thing. So these other transforms, like and for any pair of orthogonal functions, you can so define a transform. And then for a lot of these different ones, if you can figure out this supporting apparatus, you can define a Fourier-style analysis of it. That's a thing. And so when that becomes a kind of a general thing, then it helps add up for something like the operator calculus, which is like whatever fits. It's got an operator calculus. We treat derivatives and taking derivatives and integrals as operations in orders and raising and lowering rank. Just like it's so for taking powers and sums. Any of these kinds of things that make up for addition formula kind of come into the operator calculus. And so algebra has a lot going on with that. And some people say, well, this is kind of algebra. And it's like, well, yeah, if you want, but when it's not algebra and it's just quantities anymore, we can still deal with it in these other terms. They gets back and talking about algebra and quantities. It's like sometimes you can treat every variable symbolically in algebra and treat it like it's common. It's the common space of itself as a term. Other times when they become quantities, then they have the tenuous and what needs to hold them together. Quantities and terms, algebra, those. Same with arithmetic. It's deconstructed a little bit. Well, at the same time, it's like, yeah, when stuff goes to 0, you can't really get into adding and subtracting because 0 is the additive identity. Or when stuff goes to 0, you have to be careful with taking the infinite powers of numbers because 0 is the multiplicative annihilator. Different kinds of properties for the same kinds of operations of arithmetic. And the importance, again, of 0, 1, and infinity as irregular singular points of the hypergeometric ... So the idea is that there are some of these plane curves that are of interest, and they have these integral equations, and then also they have what would be singular in terms of what are otherwise the linear setups, the linear equations, which are basically considered as by what path is the line, and compared to the nonlinear, which sometimes just means spherical. And the differences between these two, in terms of the sense that one's like a continuous analog of the other, the infinite-sided polygon, a circle, and that. These are, again, kinds of things where you look to find how they can meet in the middle, because making it so incrementally always attains to that, but never gets there. So that one of the important things in mathematics is that the mathematical completeness of a rich enough object to make a continuous mapping and have a space of continuous functions has an incompleteness that's joined by some meeting in the middle of a space what surrounds them, or insofar as that it's infinite. There's a real infinity of continuity. And then otherwise it's just kind of working in terms that are defined essentially in the abstract as the discrete and the linear. So in the mathematics of the infinity and the nonlinear, in the super classical, the non-standard, the infinite case, besides where things like limits exist, and it's like, well, it's linear, that we can use a limit. Sure, that's fine. It's delta epsilon x, and I got no problems with that. but then that is later it's established that those are conventions about things, all the way down to axiomatics and descriptive set theory and axiomatic set theory, the usual model theory and meta theory of mathematics of the day. It's called the foundation. That the idea then is this continuity sits right in the foundation, and it's very natural there. That's a setting, and it gets into all kinds of the notions of the diversity and variety of constancy and variability of mathematical objects at all, that they arise from anything at all. So that's pretty fulfilling. The idea here then about the differential analysis, and so this is just kind of decompressing a bit kind of what's been studied, lastly out of this Fourier analysis about the Feher sums after, setting up the Dirichlet kernel and after the orthogonality functions. But then the following chapters look pretty cool. I'll get into that a bit because this is only page 55 of this book. There's about 500 more to be discussed. This is Lefschetz, and so Lefschetz, his algebraic geometry gets into a lot of notions of the analysis situs, which is what calculus was called before it was called calculus. It was called analysis situs, and as for Poincaré's of that and the algebraic geometry. That this is the kind of stuff that is gathering dust in Hilbert's infinite living museum of mathematics. And this is getting into deformations and infinitesimals, and then memoirs de Poincaré, orientation des varietés. La notion familière des deux sens distincts que l'on peut attribuer à un segment de courbe s'étend aux variétés bilatérales. The familiar notion of two distinct senses that one can attribute to a segment of a curve extends itself to the bilateral varieties. So this is that the bivector or the bilateral or sometimes the two form, one form and the two form. The four vector of Feynman, which is kind of like, it's a vector and it splits, and we call it a four vector. Or the multipole, anything where there's a branch or a bifurcation, this is kind of thing. And here it just speaks to that, talking about the circle as an infinitely sided polygon or an infinitely sided polygon as a circle kind of just depends on how one got there, what sense there is of this curve. That these two senses exist together, and in the middle they meet. This is kind of thing of, that's the point of this kind of dialectic, that they come together from both sides. This isn't too unfamiliar if for the definition of limit and they having to exist a limit from both sides. Because the idea of the limit, as it's generally understood, is that you take half and then half of that and half of that and half of that again and again ad infinitum, sum those up, and it goes to 1. The limit is 1 of the infinite sum of 1 over 2 to the n of n equals 1 to infinity. I think that's the most usual understanding of a limit, is that people have that is an infinite series of different sized things that has a value that is a thing. Now, for somebody, it might be more natural. It's like, well, it's kind of like 1 plus 1 over x, the infinite product. That makes e the constant of the natural logarithm. It's like, I just forgot that already, But it's Zeno's arrow paradox, and it gets halfway there until it arrives, and it's there. And while that's so, it's made the case for induction that none of the cases for induction is actually there, too. So it's a case for deduction that it arrives. So the idea is that there has to be both sides. Is that Zeno shoots the arrow into the mirror, and when it arrives from the other side, then they must actually meet in the middle. Must actually meet in the middle, because otherwise, one or the other wouldn't arrive. And so it includes the target. This is an idea of this is just an idea that the limit must exist from both sides somehow. So that's then this picking this random quote from Lefschetz about segments of curves and curves of segments, that these complementary duals must somehow meet in the middle. It's the middle of nowhere. Involves a real infinity or a completion thereof for all these things to add up together. Besides that, for in a given linear and inductive course, it gets very close. And indeed, that it's not so different than perfect in practice, but that formally there's always the other side. And that there's a place for it. That is how it works. That mathematics is complete in that kind of sense. And for various notions of validity and soundness and well-formedness of a logic, like an axiomless natural deduction arising with the language that's a comenius language, so it contains only truisms, and the only fallacy is that when you quantify over all the truisms, you get not a truism, and it's called the liar paradox, and it's only used as a prototype for absurdity. Then you have, basically, for a negatory and an affirmatory logic right atop that, this is the axiom natural deduction that a consistent and complete theory exists. Because that's like all the things in the universe. I mean, that's either it's nothing or it's the universe. Either way, they're these dual sides that flip around and complete each other. So from that, you get to like, well, is it a point or a space? Well, it's kind of like this point in this spiral space-filling curve that comes up and down into space, and that whether that fills up all the dimensions from the point first, or it's like, well, when you start with a space that's a line, it can only be split down when it's a line segment. It has kind of that it first it grows out into all the dimensions, and then it splits it back down. Well, what's the point of that? This axiomless geometry. Well, then you have points and lines. You can make Euclid's is free. What he has as axioms, you can just write off as properties of objects in this space. Then not that that's closed, because there are discontinuous objects. They're contrived. They might not be sensible, fungible, and tractable, but anything can exist in theory. Any parallel universe of bizarre, absurd objects can exist in a theory, just not in one that happens to also share the properties of being in a universe with all the Euclidean things. It's a thing. So coming into let's see, Lifshitz again. There's a lot more going on. I need to learn about varieties in spaces, because what they're going to help offer is for varieties in spaces and cycles and their connections, the divisors to zero and torsion. So divisors to zero is a kind of interesting concept. We talked here a little bit about roots of zero and then roots of the singular. That just like roots of unity, the roots of the singular have a thing. It's like, well, don't we just use Gauss's complex analysis built up over something like Euler's formula with EI pi and 1 to do everything in complex analysis? It's like, well, sure, everybody knows that, but it's not. That's just for what it is and does. If you can replace what it does and all the derivations with anything else, it's a model the same. So this Lefschitz's algebraic geometry has some of the things at least needed for that, showing that it's a model of this function, making abstract what is part of the edifice of the canon and the curriculum, because the canon is pretty much the extended curriculum vis-a-vis any mathematics, which is, you know, sensible, fungible, and tractable. Here it's that these ideas then to get into some of these nonlinear things like the torsion group. The group to torsion on G sub n minus 1 se réduit, it reduces itself to the identity. The R sub k equidistant from extremes are equal, that is to say Rk equals Rn minus k. This is a duality. A duality form is how, when it's going into the middle, and so if you meter them at pace, you know, from Zeno as the archer, he's shooting into the mirror, his image, this is where light speed is infinite, and they proceed apace and meet in the middle. There's a duality because at any point in time that it's n meters away from the mirror, it's n meters away its image from the back of the mirror, as an example of a duality. So here, when something's so for Rk and Rn minus k, because k ranges from 0 to n, that when k is n over 2, that they're the same value altogether. This duality, these are kinds of things that get into a lot of different kinds of things. There's complementary duals and the expressions of the relations of them. Models of varieties. Vano A, n dimensions, et ce cycle. Pronom le cube à n dimensions u sub n au solide défini par les relations et de formant le dans un S n plus 1 de manière à en faire coïncider les faces parallèles de chaque dimension. So set it up parallel in each dimensions. The WNs that one obtains thus are Lano n dimensions. Cette construction généralise de manière évidente celle du tour à partir de carré. Intersections of varieties and their dualities. And what those means about symmetries. The symmetries, of course, are the reflections, that when something is reflected, it's on either side. So these dualities are the same thing as symmetries. But then there's some ideas about symmetries and their invariants. That for any symmetry there exists an invariant, and in a usual mathematical model of a physical model, it's called the conservation law. Because what crosses the boundary or surface has to be maintained on one of the other sides of the surface when it's a sum on one of the other side of the surface, is like to so. That's when things are only on one or the other side. Whereas some of these duality laws are like, what happens when it's adding into the middle and ends up making an effect in the middle? What is this standing effect? How is it all standing up from all the places around it? How it is. This is what we call more like, what if it's a total field? This is a kind of a thing. This is pretty philosophical, you know, and it's just kind of trying to get into the descriptive, this descriptive differential dynamics. And to an extent to decompress this Fourier-style analysis and get into some examples of all the properties that would be necessary to establish for an entirely different set of objects the same sensibility, fungibility, and tractability to be mathematical objects of great tractability. So, reading some more from Lepsius later and learning French, which my French is so atrocious. Conditions d'existence de curve algebraique. The existence conditions of algebraic curves. This is to be followed as reflects about these steps of the integrals and many numbers. But this is to be followed some more as that it gets into what it has a lot going on from the geometer's view of the algebraic geometry. And then for the Fourier-style analysis, what I'm kind of looking forward to here is after chapter 2 where we are, which is basically just like this is the introduction. Then he gets back into the heated bar, which is Fourier's, the heated bar and the heated balls are Fourier's milieu of defining solutions for the radiation of heat and conduction. And there are other models of the exchange of heat, uniqueness and stability, endpoints, heat convection, time-independent problems, the steady state solution, the transient solution, the complete solution, time-dependent problems, exercises. Now for the time-dependent and independent problems, that got a lot into when there was reading the nonlinear electromechanical effects and applications by Mogan about the transducer and its implementation and the force that went into the vibrations, and that it's a time-dependent function which was established, which makes it so that according to the resonance of these waves and the medium, according to the configuration of the configuration space and various fixed numbers that are determined by the dimensions of the device, that it can be determined the dependency of the terms in time that end up making so they cascade or contribute to their own feedback to drive the effect of making it so that then it's predicted in an otherwise non-linear thing that it's computed. That's just getting into when there's these notions of the descriptive features of a dynamical system at all, this time dependence and time independence, where time is the only parameter. Well, there are others, but time is always a parameter. Then in terms of the steady state solution, the transient and the complete solution, in the nonlinear world, we start talking about the near field and the far field solutions, as Mogan wrote out, for an example. These being good things to know in the general checklist of a matrix of properties of features of methods for analysis in this differential analysis, these kinds of things. Then chapter 4 starts with Sturm-Liouville problems. So Liouville is pretty great. And Sturm-Liouville has a lot going on, the eigenvalues and the eigenfunctions. So here we go, the existence of the eigenvalues. So this is one of the most common means to solve differential equations. Liouville. Then the wave equation is brought in, and well, what's the wave equation? That'd be something interesting. Because, and there's another book I've been reading, one of these university mathematical texts, which is all about the wave equation. And these are pretty good. I mean, it was written by somebody from the FRS, you know, the fellows of the Royal Society, or you know, the bigwigs, as it were, over in science in the United Kingdom. That at any rate, this book on waves is something I've been looking at a bit of time, and it's something that when you start learning the vocabulary attached to all these things, kind of like sometimes it's the school of a person assigned to this field, and when you talk about them, it's to bring in their notions of their developments. And other times it's like, well, like when we talk about graph theory, there's about 50 to 100 different adjectives and nouns you should know to talk specifically about general features of a graph, which is otherwise anything is a thing, to express what kind and type it is. and what properties it has. So similarly, when you talk about the wave function, when you talk about a diagram, a graph of a wave, there are all kinds of things from the amplitude to the frequency and the wavelength and the relations to each other, and things about the definitions and the glossary of this descriptive part, the descriptive differential dynamics. It's good to have that kind of a diagram and a legend showing what is what, that then otherwise it gets put in terms of symbolically some quantities, and then those quantities are associated to the model, and then to descriptively to the model, or that the descriptively to the interpretation. Yeah, either way. Talks about the struck string and the vibrating string and D'Alembert's solution. Now we've been talking a bit about D'Alembert in the reading of this differential equations book. You know, this is INSEE or so what it is, and for Clairaut and then D'Alembert, and that's all here has been largely framed in terms of this identity dimension and fx equals y, and how that fits trivially in the Clairaut and D'Alembert, and so it's a singularity for them. It's like a zero, but instead it's kind of a line to hang other things on and transform the coordinates about it, and it's kind of a retreat from the full plane, and then making that the complex plane and getting out to the Gaussian analysis and instead just bringing it into the positive numbers and dealing with this first in this manner, figuring then you can be blown up with expansion of symmetries or what. But at any rate, when studying about the string and what happens when you put energy into it is to bend the string, and then it reaches a certain point of maximum tension at a certain point of maximum deflection, and then it's released, because the striking or the plucking, as fast as that occurs, and then how fast it's let go, arrives, then it's oscillating and restituting. It's oscillation restitution is as it vibrates back and forth, and then the attenuation and dissipation is that as the energy of that sound is so evinced from it, that attenuates as it dissipates, because the oscillation and the restitution in this case kind of oscillates, and it consumes some energy to oscillate, and thus it emits sound and radiates sound, and so what's interesting though about that is that then these combinations make these higher order resonance and waveforms, and so there's always a way to think of kind of like a string in a bubble, so the sound can't get out. It's just an example, and particularly when it's basically to make the wave fill the thing. Now this won't happen in a usual configuration because the wavelength would be too great, and the string would have to be infinitely tensile strength, yet but when you pluck it, it actually pulls the string so far, it deforms the string. So this is as that the given path through the maximum amplitude extent of the wave is more than the string at rest. So every time that the guitar string is played, it deforms the string, and that as it reaches back to its least deformed state, it radiates sound, and it happens to be about a particular frequency because of the gauge of the string and the length of the string, and to an extent how much is radiated, how it starts, this kind of thing. Long story short, One way to look at the plucking of the string is that it's a discrete action. So it just starts the string humming according to the length and the gauge of the string. And the strength of the pluck is the amplitude. But another one is like all the infinite dimensions of all the infinite degrees of all the infinite differentials of acceleration and on out, the impulse, and that there's a kernel about this of what is the completions of all this construction of the pluck, the as it struck the string is a completion of an infinite series of those out of their operator calculus. Well, what's the point of that? That seems nonlinear, and isn't that way too much work when all you have to do is measure it when it's at its maximum and let go at once as fast as you can, and it will just go off? So like, yeah, but it's not important that's not the easiest way to do it. What's important is that that's the real way it does it. Because in higher order applications, the nonlinear makes that start to get relevant. So and when we think about the potential theory, and again, this is not so much about descriptive differential dynamics, except kind of like Einstein puts it, he's like, all the universe is a total field theory and it's all differential. Fill in the rest. You know, this is part of the rest because it's about all the potential theories that make it so that this string at rest has this potential to be deformed, and when it does, it will gain energy until it breaks. You know, crime bone. Until the string breaks, it will gain energy and radiate it out into the potential. It's always potential. It's all systems of potential in these linear and nonlinear or spherical and non-spherical, you know, systems and their completions these ways. So that's what I want to talk about relating the notion of acceleration and deceleration as the impulse that goes into accelerating at all. Think of Zeno's archer's paradox. It's usually framed in one thing. It's like the archer unleashes an arrow. It flies at a constant rate, the arrow's path through the air, say 300 feet per second, very fast for an arrow. You know? And in a second, it's covered 300 feet, assuming it maintains a constant velocity and is airborne, and that it's linear in its passage, and ... It's constant and linear, right? And similarly, Achilles and the tortoise, they start out the race going at Achilles is going at Achilles' lope, and the tortoise is going at the tortoise's lope, or pace. And the differences that they have are just relative differences in their velocity. They each have their own relative velocity. But when it comes to starting and stopping, when the runners start the race, they start the race at rest. It's not a rolling start, say. It's just at rest. So it's the same kind of question to break down. How can they move with uniform motion from 0 to 1, as how can they move from 0 to 1 in velocity, so in displacement, in velocity, in acceleration, in higher order acceleration, the impulse of this kernel what results this rest exchange momentum occurs, this is part of the singular analysis and gets into the constructive account, extending our other ones. Here's Zeno's paradoxes of motion, or rather, frameworks for continuous motion, as Zeno's paradoxes of velocity, Zeno's paradoxes of acceleration. That then, in terms of velocity and the motion and the rest, and how the usual Newton's laws of zeros are first and second, body motion stays in motion, body rest stays at rest, and their inertia, right? Coming down from infinity, the start and stop of these things is bringing to relative velocities that are same, because, like they say in relativity, all velocities are relative. But when two objects come together and have the same velocity, they meet. It's a thing. And similarly, when they part, it's a thing. These are the kinds of things that get into why it's good then to know what goes into the developments of all the linear developments and all the historical setting of this, the applied analysis and the differential, so that then when these descriptive differential dynamics of the nonlinear, of the superclassical, of the continuous, as the potential theory, and also as in effect and is real and correct, they add on to it intuitively, to then know from the derivations that had to go into effect to make up all these things that are otherwise sensible, fungible, and tractable, that it ends up being the same for these as well. And that's why it's so great. Well, all right, I guess that's enough for today. Hey, have a great day. And I hope this finds you well with you and yours. And well, the moon is nice and full tonight. It's aligned pretty much so that that the face in the man in the moon is upright. All right, hey, have a great day.